Welcome to RF transceiver design course. We are discussing a low noise amplifier design, and up to now we have discussed low noise amplifier design by using S parameters, and we have also seen that if only the MOSFET we try to concentrate, because that is a widely used technology for RF receiver design. Then we have also defined for MOSFET what is a noise figure and how the noise figure is has an impact on the FT. So, that we have already discussed in the last class. Now, in this class we will try to develop few topologies and try to find out the noise figure of the same. So, LNA design requirement broadly, we as I discussed in the last class, it should have a broadband input matching if we target the higher band, or if we have a narrow band also input matching is important, because the low noise amplifier is the first component in the receiver chain. So, that is why it is important to have a impedance matching. It should have a sufficient gain to suppress the noise of the mixer, because as we know the Friese formula F, which is F1 plus F2 minus 1 by gain, as the mixer has gain of a first stage. So, we should have a very low noise figure of the first stage and the higher gain of the first stage, so that it will nullify the effect of the noise of the preceding stages. Low noise figure to enhance the receiver sensitivity. As we reduce the noise figure, we can improve the sensitivity. We have already discussed about the sensitivity in detail in the previous modules. And if we are targeting the low power application like IoT, we should also try to get the means lower power consumption to increase the battery life. And on other side, because there is a cost is involved in the size of the chip, we need to have a minimum die area in order to have the reduction in the cost. So, now let us see what are the different kind of topologies studied and available in the literature. So, if we see the MOSFET is a, so mostly we consider a 3 terminal, it is a 4 terminal device, it has a body also. But if we consider the basic configuration of the MOSFET, it has a 3 basic configuration. One is a common source, common gate and common drain. It is also called as a source follower, but this is mostly because it is only going to give you the gain in the range of 1, and it is widely used for the buffer application. We are not going to see this common drain, but all the low noise amplifier which is made from these two topology, common source and common gate. So, if we try to classify the LNA based on the topology, the first is a common source LNA, second is a common gate LNA. We also discuss the inductorless LNA because it is an application. As we discussed in the first slide, that we need to reduce the area, and while discussing the inductor, we have already studied that a inductor is taking a more space on chip. So, how you can make a design which is a inductorless, and there are noise cancelling circuits. So, in common source we will try to see resistive feedback, inductive source regeneration, cascode common source LNA with a inductive degeneration. We will also try to see the cascode common gate, then common gate with feedback, common gate with a feed forward one. So, all the common gate, so basic common gate configuration, and then inductorless configuration. The main advantage is common gate LNA with GM boosting technique. This is a widely used noise cancellation technique, and there is a inverter based inductorless LNA are also possible. In noise cancelling, we will discuss a resistive feedback noise cancelling and common gate common source noise cancelling LNA. So, let us start with the simple resistive terminated common source LNA. So, whenever you see any circuit, as a RF designer, you should know that what are the noise sources in the circuit. So, basically the input impedance means if we try to see the input impedance at the gate side, it is a very high impedance. And what is the simplest way, because we are going to connect the our amplifier, low noise amplifier with the antenna. So, we need to have an input impedance which is a 50 ohm. Now, if you try to see the MOSFET only from the gate side, the input impedance is very high and that cannot match with the antenna impedance of 50 ohm, and there is a so much reflection. So, we already have seen that if there is a no impedance match, there is a reflection will occur. So, what is the simplest way to do the impedance matching is to connect the RP resistor in parallel to the input of the MOSFET. So, here when you connect the resistance RP in parallel, that will decide your matching. So, here your input impedance or input resistance is equal to the RP. So, whenever we try to solve the any circuit for the low noise amplifier, we will the two is more important parameters. One is the impedance matching, another is the noise figure, and third is the gain. So, for this circuit your input impedance is R in, which is equal to RP, and the if we want to get the gain. So, if you just see the if there is a voltage here that is given by V in, if this is a V in, this is a Vs. So, your because and we want Rp should be matched with the Rs, and if Rs and Rp are same. So, if Rs is equal to Rp, that leads to Vs V in, which is equal to Vs by 2. So, the first disadvantage of this circuit is, as there is a resistive matching, what is happening is that the your half of the power, half of the input voltage at the input side itself, it is a coming half. So, because of that, the your 50 percentage of the gain is reduced here itself. Now, the gain we can write in terms of Rp and Rs. If Rs and Rp are not equal, we can write Rp by Rp plus Rs into Gm into Rd. So, this is a gain of the circuit. If you consider Rs is equal to Rp, it is equal to Gm Rd by 2. So, your gain will be half because you have used a resistive matching and there is a resistive load. So, as I told, now noise figure equation we already know. So, as discussed while discussing the noise figure is nothing but SNR in by SNR out. So, I can write it down it like this: Si by Ni into No by So. That can again decompose in terms of Si by Ni into No by G into Si, where Si is a cancel out. So, if you try to see the input noise Ni in this case, So, mostly this is 4 kTRS into NO, that is a total output noise, and it can, if we try to represent in terms of the mean square voltage noise power spectral density divided by gain square, because here we have considered the square, here we are considering it as a gain square. So, this is how we can find out the noise figure. So, for this what we need to have, we need to find the V n square out. So, how can we find out the V n square out? So, because there are RS and RP which are parallel, if there is a no source, we can directly write the noise due to RS and RP. So, what is the method to find the V n out square? First we need to find that how many noise sources are there in the circuit. So, can you think how many noise sources are there? But obvious, there are 4 noise sources, one is due to RS, one is due to RP, another is a MOSFET, and then load resistance RD. So, in order to find the V n out square, mean square, what we need to consider, we need to use a superposition theorem, and for each noise source we will try to see the what is the output noise, and then we will add all the noise to find out the V n out square, mean square. Then we already know the gain of the amplifier, we divide it by gain square and 1 by 4 kT RS. So, this is a methodology that we will try to use. So, as RS and RP both are in parallel, we can directly write for RS and RP, that is noise due to RS and RP, it is given as a 4 kT RS parallel RP, and because the whatever noise source RS and RP, that noise is going to amplify by this amplifier. So, we need to add the gain also, that is a Gm into Rd whole square. So, this is a noise due to RS and RP. Now, noise due to the transistors M. So, that is 4 kT. So, if we see the current, that is 4 kT gamma Gm noise current, that we have already discussed, 4 kT gamma Gm current, that is a thermal noise, and it is given as a 4 kT, and we are interested for the voltage, because here the term is V n square out. So, we are multiplying with the Rd square. So, noise square root noise current is multiplied with the Rd square. Now, noise due to Rd, which is equal to 4 . So, here we are not adding the gain, because that is a at the output side only, it is not going to amplify. So, we are just considering 4 kT into RT. Now, what we need to do is, we need to put all this in this equation, then we will get the noise figure. So, which is equal to 1 by 4 kT RS, then 4 kT RS parallel RP into GM RD whole square plus 4 kT gamma GM RD square plus 4 kT RT. 4 kT RS is already there, gain square. So, when we consider the gain here is GM into RD whole square, and we also need to consider RP square RS plus RP square. Now, we will take each term one by one. So, the for first term, that is if we consider the 4 kT is a common in all, we can cancel it out from the top and bottom. So, 4 kT is common in all, so that is cancelled out. Then we can write here RS RP by RS plus RP into GM square RD square by RP square RS plus RP square into GM square RD square. Same we can also write for here gamma GM RD square GM square RD square this is RD and RP, do not confuse, RS plus RP square. Then we will have a and we also need to consider everywhere there is a RS, because we just cancel out the 4 kT. So, then RD by GM into RD square into RP square by RS plus RP square. So, here RS is multiplied. So, now we will try to cancel out the term that we can cancel. Here it can be, this can be easily cancelled out, and then we can also cancel out the RS, we can also cancel out one of the RP, and we can also cancel out the RS plus RP. So, what remains that we will write it down in the next slide. So, then noise figure is given by RS plus RP by RP. So, as RS plus RP by RP. This is the first term, we can write 1 plus RS RP. Now, in the second, this RD is cancelled out, this RD square, one of the GM is cancelled out, and if we multiply RS at the bottom and RS at the top, this we can write it as RS parallel RP. So, another term, that is a gamma into gamma by gamma RS into RS square RP square by RS plus RP whole square, plus here we can cancel out the RD. So, RD is cancelling out. So, if this is GM square and if this is RD square, one of the RD is cancelled out, and we will have a RS by GM square RS parallel RP square into RD. So, same thing is written here, GM square and RS. So, RS we have multiplied at the top and bottom. So, it is RS parallel RP. So, finally we can write the noise figure, which is gamma RS by parallel RP square plus RS GM square RS parallel RP square into RD. Now, we will take, if, because we want to have impedance matching, RS is equal to RP, the noise figure can be written as a, this RS is equal to RP. So, 1 plus 1 plus, because RS is equal to RP, we can write RS by 2, and that will come as a RS square by 2. So, we can write that is 4 gamma GM into RS, because there is a RS square. So, because RS square is there, RS can be cancelled out, plus we will have a RS by GM square RS square by 4 into RD. So, this 4 will go up. So, we can write it as a, this is a 2 plus 4 gamma GM RS plus 4 by GM square RS RD. So, this is very important equation. It will tell us many things, that this configuration minimum noise figure, if we try to neglect this term also, then noise figure is a 2 and that is a around 3 dB. So, that will be very high noise figure, and the minimum noise figure is a 3 dB, it will go more than this also. So, for low noise application we cannot use this structure, but it has, let us say if you have a not that much stringent noise figure requirement, you can use this amplifier. It has one advantage, that is because, so the disadvantage is noise figure is too high, greater than 3 dB, and advantage is uh, broadband matching because it is a resistive matching, and mostly the half of the power is reduced, the gain is also less. Gain is less than 3 dB, less than 3 dB of the desired, let us say if we, because at the input side itself there is a half of the voltage. So, this is about the uh, common source amplifier with resistive matching. So, there is one more advanced circuit that we can try to look after, that is a, if we do the resistive feedback from drain to gate, that is also widely used circuit. So, this if we try to draw the circuit, that is a RF feedback, and if there is a capacitor, that is a DC blocking capacitor RS, there is a Vs, this is a ground. So, this in this advantage is in this structure that your in the previous topology we are our voltage is half at the input side, here the voltage is not a half, and if you see, as this is considered as a diode connected, your input impedance, that is R in, is equal to 1 by Gm of this MOSFET. So, it is a straightforward, R in is equal to 1 by Gm, and if you try to match, R in is equal to Rs, which is 1 by Gm, and if you are targeting the 50 ohm impedance matching, that is Rs, then Gm you need is around 20 millisiemens. So, if we if we want to find out the gain of this circuit, it is a simple, we just take this as a RF. If there is a voltage Vx at this side, then we will get Rf Gm into Vx. So, this is a Vx here, and then this is a V out. So, we can get directly Vx, if this is a Vx, minus Gm into Gm Vx into Rf equal to V out. So, V out by Vx is given by 1 minus, and if we try to put the Gm is equal to 1 by Rs, it is Rf by Rs. It can also be because the same here the input impedance is 50 ohm. So, same we can also write the V out by Vs is equal to half one minus Rf by Rs. We can also mention it as a minus because if this term is a higher, minus Rf by Rs into half. So, this is a gain of the amplifier. So, as we discussed in the previous example, what we need is the input impedance, gain, and we also need a output impedance, because in this case it is not a straightforward. So, we also need output impedance. So, this is a for input impedance, this is for the gain, then input impedance. Now, we will try to find out the output impedance. So, for small signal, if this is a RS and the input is grounded, there is a VGS, and here there is a RF. We will have a current GM into VGS and V out. VGS we can also mention as a Vx, because we have already mentioned here as a Vx. So, this here we can directly write the KCL V out minus VGS by RF plus G, because we are interested to find out the output impedance V out by I out, GM into VGS is equal to I out. So, VGS we can mention it as a RS by RS plus RF into V out, because there is only one potential V output voltage V out is there. So, we can write VGS, which is RS by RS plus RF into V out. We will directly get then this is, if we try to put the VGS in this equation, we will get V out one minus RS upon RS plus RF, then GM RS RF into V out into I out. So, if V out we take it out, take on this side, we will get 1 by R out is equal to, because if this term will go up, that is 1 by RS plus RF, because there is RS also in the denominator, 1 by RS plus RF plus 1 by GM into 1 plus RS RF plus RF by RS. So, if we try to make RS in this case denominator, so that is 1 plus RS by RF, if GM also in denominator, so we can directly write R out is equal to 1 by GM 1 plus RF by RS parallel to RS plus RF. And this term implies, if we consider GM is equal to 1 by RS, the R out will come out as a RF plus RS by 2. So, now we got everything. We have a input impedance, we have output impedance, and we have a gain. We will try to use the same formula of the noise figure, and we will find out the noise figure in the next class. Thank you.